What is quantum computing? It's a new way of computing using quantum bits, or qubits, instead of traditional binary bits. And it's 158 million times faster than the most sophisticated supercomputer available in the world today. In fact, it's so powerful that a quantum computer can complete a task that would take a traditional supercomputer thousands of years to do in just 4 minutes. Right about now, you're probably thinking, what? How is that possible? It's possible because quantum effects, a result of the rules that govern nature at the subatomic level, are very, very weird. When we write algorithms that apply these quantum effects to the qubits in a quantum computer, they can evaluate a mixture of possible outcomes rather than considering one at a time. Classical computers, or as I like to call them, all the computers you have ever used in your entire life so far, can only perform one calculation at a time. All the computers that power the cloud, all the corporate world, your internet provider, and your smartphone, all classical. That makes them unsuited to address certain intractable problems that require the kind of mathematical processing that only quantum computers can do quickly. In the future, with quantum computing, we can solve problems that are now beyond us, like how can we optimize the global supply chain so events like COVID don't destroy the economy? How can we design and develop new drugs quickly and safely? And how can we predict natural disasters and hurricanes before they happen? What is quantum computing? It's the future. What does a quantum computer do? It uses qubits that can represent a multitude of possible quantum states and performs operations on them. Unlike the bits of classical computers, which can only represent one state at a time, quantum computers are free of sequential constraints. Think of the old phrase, looking for a needle in a haystack. That's the perfect description of an intractable problem. If the needle is the solution to your intractable problem, and the stalks of hay are all the millions of non-solutions to it, how do you get it solved? A classical computer would have to look at each piece of hay one at a time and determine if it's a needle. Is this a needle? No. Is that a needle? No. What about this one? Again, no. It would take us ages. A quantum computer could metaphorically shake up the contents of the haystack and examine everything in it in a short period of time. Of course, first you have to write an algorithm that tells the qubits what you're looking for. With that algorithm running, the quantum computer can identify likely needles and discard everything else. When it's done, the quantum computer has identified a smaller, more manageable collection of things that have a high probability of being needles. Then you can bring back your trusty classical computer to do a sequential analysis to discover which of the smaller collection is actually the needle. So don't count out classical computers. For most computational problems, the sequential format of classical computing is just fine. You can relax. You're not going to need to replace your phone or laptop anytime soon. But for intractable problems that have thousands of variables and millions of potential solutions, you need a quantum computer. Or you could just wait thousands of years while your classical supercomputer runs through each possibility one at a time. What do quantum computers do? They solve intractable problems when you don't have millennia to spare. Why does quantum computing matter? It matters because quantum computers have the potential to disrupt nearly every industry. It could transform medicine, break current encryption, and revolutionize communications and artificial intelligence. And honestly, we are on the cusp of quantum advantage. That's why governments, businesses, and scientists are taking notice. At the same time, classical computers are beginning to reach their physical limitations as new technologies like machine learning and artificial intelligence demand more computing power. Quantum computing is needed so machines can learn from more complex and more diverse datasets, calculating more efficient outcomes. Let's not forget, classical computers struggle modeling natural behaviors at a quantum level. Things like chemical reactions, biological processes, and material formations often involve quantum interactions and need to be investigated using quantum computers. Right now, we are in the NISQ era of quantum computing. NISQ stands for Noisy Intermediate Scale Quantum. Noisy refers to improving the signals on the quantum chip. Intermediate scale means we need more qubits that can do more operations to run very large problems. Even on NISQ computers, companies are starting to see benefits. Once we scale quantum computers, we will see more quantum advantage. Why does quantum computing matter? Because once it happens, everything will change. How is quantum computing applied? We use quantum computing to address intractable problems that can't be addressed with classical computers. Intractable problems are everywhere, but there are 3 types that are well suited to quantum computing: optimization, machine learning, and simulation. The goal of optimization is to find the best solution out of a great many, even millions of possible solutions. Opportunities for optimization include devising the fastest and most cost-effective transportation routes, finding the most efficient way to schedule workers, and determining the best organ transplant pairings in a donation system. The second kind of application is machine learning. It is the core technology that allows machines to mimic the way humans learn and execute tasks. Machine learning is based on both optimization and sampling methods. Sampling helps us understand and simulate processes that are random in nature. Quantum computers are more efficient at sampling from systems that are highly complex and even quantum mechanical. The third kind of application is simulations. Simulations of molecular processes can only be modeled as quantum systems, so quantum computing could revolutionize the way we research and discover new drugs. Quantum computers, which are faster and can handle more complex relationships within data, are a perfect choice for this type of work. Quantum computers can be applied to some of our most intractable problems. How does quantum computing work? We'll get to that in a minute. Let's start even more basic. What does a quantum computer look like? Since we're still in the early days, there is no standard quantum computer design. But a common feature of most quantum computers is that qubits are housed in chips. Those chips live inside what we call a chandelier because, yeah, it looks kind of like a chandelier. The chandelier is housed inside of a super cold refrigerated barrier that protects the qubits from our noisy and warm environment. This is what one type of quantum computer looks like. Now let's talk about how it works. The best way to do that is to compare a quantum computer with a classical computer that we use every day. Classical computers do their calculations using transistors or bits. Each bit can have a value of 0 or 1, not both. It's a strictly either-or situation. Quantum computers calculate with qubits or quantum bits. Unlike classical bits, qubits can represent both 0 and 1 at the same time. We call this ability to be in multiple states at once superposition. Superposition is one of the quantum effects that make quantum computing possible. Classical computers, because their bits can only be 1 or 0, can only process one computational result at a time, sequentially. Think of it like playing a trumpet. You can only play one note at a time. A quantum computer can process a mixture of computational results. It's like playing a piano. You can play several notes together, making a chord. Classical bits are individual and have no relation to one another, but qubits can be entangled with one another. Changing the state of one entangled qubit will influence the state of others, regardless of their distance from one another. This is called entanglement, one of the quantum effects that allows quantum computers to do what they do. The output of classical computers is deterministic, meaning there is only one outcome. The output of quantum computers is probabilistic, meaning that there are multiple possible outcomes, some of which are more likely than others. Classical computers have low error rates. Quantum computers have relatively high error rates because it's a new technology and its environment requirements are intense. This error rate will decrease as the technology matures. Classical computers can operate at room temperature. Quantum computers can only operate at super cold temperatures, colder even than the frigid vacuum of outer space. That's because to a quantum computer, heat equals noise, which boosts error rates. And lastly, classical computers can store data indefinitely. Quantum computers don't have memory. The results are reduced to ones and zeros and stored in classical memory. How does quantum computing work? By taking advantage of quantum effects like superposition and entanglement to arrive at a probabilistic set of possible outcomes. How does quantum computing combine with other technologies? It will have an impact on many TQ technologies. Let's look at just 4 of them. First, cloud. Quantum computers are too expensive and delicate for most businesses to have their own machine. So most of them will use a cloud-based quantum as a service model from companies like IBM, Microsoft, D-Wave, and Rigetti. Next, quantum and artificial intelligence. Quantum has the power to improve AI performance. Traditional bottlenecks in processing hard problems could disappear, allowing machines to learn much faster. Third, security. Quantum computing will solve many business problems for sure, but there is a likelihood that quantum will make conventional encryption more vulnerable to attack. A reliable, high-quality quantum computer could easily break our current cryptographic protocols. That is why the race is on to create post-quantum or quantum-resistant cryptography that can replace modern standards. And lastly, quantum computing and sustainability. One bright spot in our fight to reverse global climate change is quantum's potential to speed up sustainability research. The United Nations has identified 17 goals for sustainable development, and quantum computing could make a big impact on at least 4 of them. They are zero hunger, good health and well-being, clean water and sanitation, and clean, affordable energy. Quantum computing, it's going to change the game.